Okay, I'm back. Now is the microphone working? Am I coming in loud and clear? Thank you. Okay, so I actually broke the microphone this morning. Not the microphone, the battery inside it. I dropped the microphone. No, I didn't mean to do it. I just knocked it off the table, and yeah, I actually smashed the battery. So yeah. Anyway, all right. So let's try this again. Um, Differentiation today, and a lot of it will be familiar, which is good. A few small things might not be familiar. Um, don't forget, summertime starts in Sydney on Monday. So, actually, it's Sunday, but so you have to get to the lectures 1 hour earlier. All right. So let me share my screen with you, and we can show you what's happening. All right. So today is differentiation, and it's reasonably introductory, and I hope you remember like a lot of it. If you've forgotten it, not a problem. Um, we're going to look at the derivative as a limit. Now, this might be new to you, okay? And these kind of questions are favorite questions that you might see on an exam or a class test or something like that. The computing derivatives is probably familiar or old, and this stuff is probably new. The relationship between continuous functions and differentiable functions, or differentiable functions and continuous functions. Remember, last week we talked a lot about continuous functions, okay? So, Anubhav, I don't know if it will update in the calendars. I hope it will. I hope it will. So I'm just letting you know. All right, derivative of a function. So you have something like y equals a function of x, and that you can write the derivative like this or like this. So you can put a dash or dy dx. They're both okay. And as you probably remember, derivatives give us a way of calculating rates of change. Okay, and derivatives are what it's basically half of calculus. Okay, so you have the derivative of a function, you have the integral of a function, and together they make up calculus. Okay, now if you study physics or applied math, a simple relationship is the following. If this represents a velocity, then and you differentiate it, then you can compute the acceleration. All right, so the derivative as a limit is a pretty important concept for this course. Okay, so what we would hope you could do is get familiar with how you compute the derivative as a limit. And if you're given a function and you want to compute the derivative, well, you can do that using a limit. In fact, this is actually the definition of the derivative. So you've got a function, and let me just turn that brightness down a bit. And you look at this quotient and you take the limit as h approaches 0. That's actually how we define the derivative, right? We don't always use this to compute the derivative, but this is actually how it's defined. Okay, so in this picture, if this is a graph, the red, that's your curve, the red points, and you can see here we've got a tangent line to the graph at x equals 2. Okay, so the gradient or the slope of this tangent line is geometrically the derivative of the curve at x equals 2. So That's what it means geometrically. So we would denote that by this. Okay. So we define this derivative as using this limit. Geometrically, it's just the slope of a tangent line at the point of interest. We're going to look at this with some examples and see how we can compute these problems, solve these problems. All right. So I'm just going to keep this here because we're going to use it down here. All right. So if you think back to the rules, there are some basic rules for derivatives, right? Like you should really be familiar with these. Okay. We'll look at those in a minute. But this question asks you to use the limit definition. So they want you to use this definition on the other page. Okay. Now, we know, who can tell me in the chat, what will the actual answer be? What is the derivative of x squared minus 4x? Who can tell me? Alan, yeah, Anna, exactly. It'll be 2x minus 4, but they actually don't want that. Yeah, so the 2 comes to the front, you decrease the power by 1, and the same over here. Okay, so we know that that is equal to that, but they want us to use this limit definition. So there are a few strategies with doing these kinds of problems. You start with this and you simplify, and the very last thing you do is take the limit. Okay, that's how I usually do it. So a lot of these kind of questions involve algebraic simplification. Okay, so you start with something, you simplify it, and the very last thing you do is take a limit. Okay, that's the very last thing you do. So let me show you how you do it, and we can work through this problem. All right, so here, your function of x is just x squared minus 4x. And so we've got that, no problem. Let's get this now. Okay, so what we do now is replace x with x plus h in brackets. So it's going to be x plus h all squared minus 4 times x plus h. So we'll use these two expressions in here and try to simplify and eliminate that denominator, the h. Okay, so now the algebra starts, and the very last thing we're going to do is take the limit. Okay, so I'm not taking the limit there. All right, so it's going to be x plus h squared minus 4 times x plus h minus f of x. And the challenge is to get rid of that h and simplify everything. Okay, so one way you can do is just actually expand all the brackets and look for the simplifications. You can also do difference of 2 squares here if you wanted to, but I'm not going to do that. I'm just going to write it all out. So we get a mess, and hopefully we can simplify. So that's going to go with that. That's going to go with that. And we've got these 3 terms left over. Okay. And you can see, oh my goodness, there's a common factor of h. So what I can do is factorize. And before I take my limit, cancel. And the last thing I'm going to do is take that limit. We know it should be that. As h goes to 0, this disappears. So hence, okay, that's going to go to 0. Oh, there we go. Whoops. There we go. Now that is a very long but completely rigorous and detailed justification for computing or for computing the derivative here and showing it there. Okay. Yeah, Daniel. So h. So you can see what does h mean? H is just a small distance away from the point x. Okay, so x plus h will be a little bit different here. So if I was to draw a little picture, right? So if this is, let's say, x, then x plus h in this picture might be over here, right? H could be negative, so you can have one over there as well, right? And so what this does is you squeeze that as it goes to 0, you squeeze that, and this thing actually turns into the tangent line. Okay. Doesn't have to be in closed brackets, James. I never said it has to be in closed brackets. If you want to put them in open brackets, it's fine. It's just multiplication. Like I'm just grouping all these all together. It's not an interval. Okay. Yep. So yep. So you squeeze that, and you divide it by h, and it turns into the tangent line, the slope of the tangent line. Okay. Yeah. So with these, the strategy is always the same. Do some algebra, simplify, and the last thing you do is take the limit. Okay. The last thing you do is take the limit. So there's lots of examples like that in that you'll see in tests, and you'll see also in like your weekly quizzes and maybe even lab test 1. All right. The derivatives and geometric properties. So you probably remember this as well, that f be a function on some interval. If the derivative's positive, then f is increasing on the interval. If the derivative's negative, then it's decreasing. And if the derivative's 0, then the function's not increasing or decreasing, it's just constant. Okay, so if you look at these sort of points here, you can see on this interval, the function's increasing. On this interval, the function's decreasing. And on this interval, the function's increasing again, okay? And so one way of looking at that is the slope of the tangent line positive or negative? So if I draw in, say, a tangent line there, I definitely see the gradient of that tangent line is positive, right? If I draw one in, say, there, the gradient of that tangent line is definitely negative, and the gradient of that tangent line is definitely positive. And that's true for all those points on that interval. Okay. All right. Hopefully these are familiar to you. If you want to compute derivatives, well, you could do that, but that takes forever, right? And it's not necessary unless you're specifically asked to do it. You can use these, the limit form of the derivative, to actually justify all of these things here. Okay, and the proofs are in your course pack, the calculus notes. Okay, so I won't prove those today, but just as an example, you know, if I differentiate a power function, well, I bring the power to the front and I decrease the power by 1. If I'm differentiating an exponential function, well, the derivative doesn't change. If I'm differentiating the sine function, I go to cos, and if I differentiate cos, I go to negative sine. And there's a couple more when you're differentiating trig functions. So the proofs are in your calculus course pack. But let's see how it works with a simple example. We want to differentiate this function here. Here's a power function. This also can be written as a power function, x to the 1/2. Another power function, x to the -2, and a trig function. Okay, so the way I like to do these problems is just to break them up into 1, 2, 3, 4 parts. Okay, so with the derivative, you can break this part up into 4 parts. So I've written 1 on x squared as x to the -2 there. Okay, so if I wanted to differentiate this, well, it's 4 times the derivative of x cubed. So the 3 comes to the front, it multiplies with the 4, and you'll get something like that. With this one, the half comes to the front, you decrease the power by 1, so it will be something like this. Oops. So instead of having 1/2, you decrease it by 1 and you get -1/2. Down here, the -2 will come to the front, so you'll get +2 at the front, and you decrease the power by 1. And sine goes to cos, and you multiply by -2. Okay? So these are the really simple, everyday kind of derivatives that you hopefully remember, or these are the entry-level kind of problems. That you won't see very many problems like this, okay? Because the course is really assuming that you're comfortable with these basic moves with the derivative. All right. So something a little bit more challenging. You probably have seen these things before. When you're differentiating the product of 2 functions, you have the so-called product rule. When you're differentiating a quotient of 2 functions, you have a quotient rule. And when you're differentiating the composition of 2 functions, you have a chain rule. Now, the chain rule here is a little bit like there's a few ways to write it. So I want to write it a couple of different ways, because I know some people prefer this dy dx notation instead of this dash notation. So let me give you an alternative formula for the chain rule. Okay, so if y equals f of u, and u equals g of x, then the derivative is just the product of these 2 things. Okay, so some of you might have seen this formula before, or this form. So basically you can treat the differentials like fractions. They're not really fractions, but you can cover those up and go, dy dx. Now it's not. Now you see it, now you don't. Now you see it, now you don't. Okay? If it's more than 2 terms and above, then you would have sort of 3 things here, right? So that's easy. That's not difficult to do. So if you had a function of a function of a function, then you could say that's that, and then x depends on something else, and you would have 3 things over here. Okay, that's not a problem. Okay, great question, by the way. Okay, so let's compute the derivative for this product. Okay, it's a product, right? So I could let u be e to the x and v be cosine x. All right, so let's look at our product rule. We need four things: u, v, u dash, and v dash. Okay, so if u equals e to the x, if u equals e to the x and v equals cosine x, then what's the derivative of this? Well, u dash is just e to the x, and v dash is negative sine x. So it's that times that plus that times that. Okay. All right. So by the product rule, the derivative of e to the x times cosine x is that times that plus that times that. Okay, so let's second one first. E to the x cosine x minus e to the x sine x. And you can factor out the e to the x if you like. Okay, there you go. Okay, so that's a pretty simple product rule. You'll find the product rule is very helpful when you want to do part of a question, like you need to compute something quickly and then use it for another part of the solution. Okay, what about the quotient rule? Well, let's have a look. Apply the quotient rule. Now, the question is, right, here it is, here's our function. Is it necessary to use the quotient rule there? Could I somehow use maybe the product rule? Do I have a choice here? Is it like, it looks like a quotient, but could I maybe write this another way? Yeah, so you could write this as a product if you really wanted to. Okay, so I'm just looking at the chat, and a few people are saying, yeah, we could do that. I mean, one way to do it is just to write it like this. Okay, and say, oh, that's going to be, you know, u, and that's going to be v, or something like that. But you do need a chain rule there, right? Because you've got a function of a function. So let's put this down with and do it with the quotient rule. So here the u will be on the top, and yeah, Hawk, exactly, Hawk. That's what I'm thinking too. So if u is sine x and v is x squared plus 1, the dash is going to be cosine x of u. And v dash, if I differentiate x squared plus 1, it's just 2x. Okay, so for my quotient rule, I need four things: u, v, u dash, v dash. Okay, so let's apply this, and we can compute the derivative. So it's always good to mention the rule or the idea that you're using. So we have, by the quotient rule, it's going to be v x squared plus 1 times u dash, which is cosine x, minus u times v dash. So u is sine x and v dash is 2x. And that's all going to be over v squared. So you square the denominator. That's it. Okay, so you could apply the quotient rule here. You could apply, it's possible to use the chain rule. Okay, but I think it's actually easier to use the quotient rule, because to use the chain rule, you've got to differentiate this, and you know, that will take some time. But the thing that I'm trying to say here is that sometimes you have a choice which method you want to use. Do I want to use chain product rule? Do I want to use quotient rule? What works best for me? I think that's really important. Okay. All right. Okay, let's do a chain rule one. Okay. There. Okay. So here we've got a function of a function, right? So if we let that equal this, who can tell me the two functions at play in this function over here? What are the two parts of the function? Can anyone tell me in the chat? What are the sort of, Matthew, yes. So there's two parts. Nice square root sign too. There's like an inside part, which is 2 plus x squared, and then there's an outside part, which is the square root. Yeah, so Steve, you're on it. Hawk, Hulan, yes. So the inside function is like 2 plus x squared, and the outside function is the square root function. Okay, so what I'll do, I'll actually solve it using this second handwritten form, because I think it's actually easier. Okay, so I'm going to let u be the inside function. So y equals the square root of that, which is just the square root of u. So I'm going to differentiate both of these parts separately and then multiply them together. Okay. Okay, so I'm going to say, right, do y du is the derivative of this. So here I'm differentiating with respect to u. It's a power function. Bring the half to the front and decrease the power by 1. Okay. So that's the first part over here. Let's get this part now. If I differentiate this, I differentiate 2 and I get 0. I differentiate that, I get 2x. So by the chain rule, I just want to multiply these two things together. So dy dx equals that times that. So obviously the 2's are going to cancel out, but they're not right here. What do I do with the u? What do I do? I don't know. What do you do with the u? Anyone tell me what happens with the u? Let me know in the chat. Yeah, Azalea. Carl, I think we want to get everything back in terms of x. So we take the u, put it back in here with 2 plus x squared. Okay, so okay, if you want to clean that up algebraically, we can say it's just this. Oops, 2 plus. Okay. There you go. This is a chain rule. So the 3 big ones: product rule, quotient rule, and chain rule. Excellent, everyone. Okay, now we're going to switch out of familiar territory into unfamiliar territory. Or some of you may, oh, I just smashed the microphone, sorry. Again, some of you may know the following concepts, but I wanted to spend a fair bit of time on them because I think that's where you'll see most of the assessment. This stuff here is good, but it's really sort of assumed knowledge in many cases. So I want to talk about the relationship between a differentiable function and a continuous function. Okay, really, really important. And you'll see lots of examples and exercises on this in your course packs, okay? All right. So when we talk about a differentiable function, what we mean is that the derivative and this limit exists everywhere, okay? So remember, the derivative is really a limit. So when we're talking about a differentiable function, we mean that this limit exists at the x point of interest, okay? All right. Now, there are some strategies here about where a function is differentiable or not differentiable. All right. One type of problem that you'll see involves a graph, a given graph. We don't know what the actual function is, so you can't compute the derivative explicitly, but you can try to work out what's going on from the graph. Okay. All right, so the first part, we'll move on to this bit later. Who can tell me where is the function discontinuous? If we're looking at this our old friend, this graph, what x points does this function have discontinuities? All right, so there's obviously, yeah, a point here where the graph jumps. And there's another point here where the graph jumps, okay? So the discontinuities, and people are absolutely right, and you've raised a good question, Steve. So discontinuities at x equals 4 and x equals 5. All right. So Steve's made an interesting question here about 3. Is the graph continuous at x equals 3? Who can tell me? So it is, Azalea, and Steve, because I can draw the graph without lifting my pen off the paper for this part, okay? So it's definitely continuous at x equals 3. But we haven't answered this question yet. Where is it not differentiable, okay? So a physical, geometrical way of saying where is it not differentiable, it's points where it has no tangent line to the curve, right? So it can't have a tangent line there, okay? This is known as a spike point or a corner, right? So at all these other points, I can draw in these nice over here, these nice tangent lines, but it doesn't work at x equals 3. It definitely doesn't work at x equals 4, and it definitely doesn't work at x equals 5. I mean, how are you going to draw a tangent line to the curve at x equals 5? Or does it go like that? Does it go like that? Does it go like that? There's no way you can do it. Okay, so let's summarize this and see how we go. So the graph does not have tangents at x equals 4, at x equals 5. It's because of discontinuities. So discontinuity. This is like a spike or corner. Okay, so f is not differentiable. So this is my way of summarizing differentiable at x equals 3, 4, and 5. Everywhere else, we can draw in a tangent line, right? But not at this point, not at this point, and definitely not at this point. I mean, what do you even do with that? Okay, it's not possible. Now, one of the most difficult things that students find in the calculus is to really understand the relationship between continuous functions and differentiable functions, right? They mix up the two and they don't know like the relationship if one implies the other. So let me spend a little bit of time talking about that too, because that's a really important thing for assessment. Okay, so it's contained down the bottom here. A differentiable function is always continuous, but a continuous function is not always differentiable. So if you look up here, this graph is continuous at x equals 3, but it doesn't have a derivative there. Okay? So what does a differentiable function look like? Well, it can be a smooth curve. Okay, so if I was to draw something like this, so I'm going to draw a nice smooth curve like this. Okay, so I'll just make that a bit smoother. Okay, you can ride your skateboard or something on that super easily. This is nice soft bends. It doesn't have any sort of sharp points. This is a smooth curve. And it's differentiable at all points. This one, not so smooth, right? You've got that, you've got that, and you've got that. Okay, so a differentiable function is always continuous. You can see from this graph, it's definitely a continuous function. But a continuous function, like this part, is not necessarily differentiable. It might be, but you don't know for sure. Okay. So if you can understand that relationship, then it's a win. Okay, it's a big win. Okay, last question. Is the following function continuous at x equals 0? Is it differentiable at x equals 0? So it's a split function. Remember, it's split into two parts. And in this course, we see a lot of split functions. Okay. Yeah, Daniel, can a function be differentiable over a set? Yes. It can. So here's a question for you, Daniel. What does it mean for a function to be differentiable over the interval okay, this is a question for you. Oh, sorry, that should be a question mark. Okay, think about it and come back if you have a reply. All right. So two parts. Is the function continuous? Is it differentiable at these 2 points? Okay. All right. So let me go to GeoGebra and I can share. Oh, no, window. Yeah. All right. So let me zoom in. Here it is, people. Ba, 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 ba. So just by looking at the graph, is the function continuous at x equals 0? Yes or no? Who can tell me? Who can tell me? It's definitely continuous. I think the group has spoken. It's definitely continuous because I can draw that part of the curve, and without taking my pen off the paper, I can draw that part of the curve. So it's definitely continuous, right? Second part is it differentiable at x equals 0? Is it smooth? It's definitely not a smooth transition, is it? So the answer is no, it's not differentiable at x equals 0. Okay, so this is an example that's continuous at x equals 0, but not differentiable. Okay, so let's summarize that in our solution. So yes, from the graph. No. Oops. Again, from the graph. But what happens if we really wanted to use calculus here and plot it properly and solve it, properly? The first thing we want to do is work out the limit for this. So for the continuity, we want to consider this. And for the differentiability, what we would want to do is, we want to see if this exists, this limit exists at x equals 0. Okay, so let's work through that. You've got a left-hand limit and a right-hand limit. So let me go back to our picture. Who can tell me what is the left-hand limit as x approaches 0 from the left? What is the actual limit there? It's 1. And from the right, it's also 1. And the value of the limit, the value of the function is also 1. Yep, that's great. Keep those things coming in the chat. So the left-hand limit equals the right-hand limit equals f of 0. So this joint value is that. This is also the same value. So it is continuous at x equals 0. All right, second part. Now this is a bit more difficult. We will look, I think next week we'll look at a theorem called the split function theorem. But how would you do this just using the original limit? Let me show you. What we want is this. So we want to come in from the right and the left. And we want to see, so you can see hopefully what I'm doing here. I'm taking this limit, I'm putting in x equals 0, and I'm considering the right-hand limit and the left-hand limit because this doesn't exist unless that and that are the same. So I've put a little question there. Okay. So we want to, it looks a bit crazy, but we just want to, we're asking ourselves, are these two things equal or not? If they're not equal, then the derivative can't exist. If they are equal, then it's fine. So, all right, so let's consider this. So, okay, so when x is positive, it's going to be this. So I'm going to get 2, 0 plus h plus 1. So f of 0 is just 1 there, all over h. Okay, and the 1's going to cancel out, the h's will cancel out. So the derivative is going to be 2. All right. Now for this one, it's a little bit harder. So this is where h is coming in from the left. So we want that. F of 0 is 1. And this goes to 0 as h goes to 0 from the left. Okay, so this and this are not equal. Okay, so the question now is, well, how did I know that this went to this? Don't worry about that at the moment. That's we'll look at that later. There are ways of evaluating this later. But the important thing that I wanted to talk about was this and this are not equal. Okay, so the derivative does not exist at 0. Okay, that's the same as saying it's not differentiable at 0. Okay, where is that on the difficulty scale? It's not low. It's not low. So, you know, we'll look at different tests for showing differentiability. But if you want to go back to bare basics, this is what you can do. Okay, but the most important thing in today's lecture, I think, from an examination point of view, is to really understand the relationship between, you know, differentiable functions and continuous functions, and continuous functions and differentiable functions. I think that's actually the most important thing. It's sort of a more of a meta thing. All right, folks. Correct, Matthew. Every differentiable function is a continuous function. No, hang on. No, Matthew. No, it's around the other. So every differentiable function is a continuous function. Yes. So you're correct. So I've turned on people's microphones if they want to have a chat or ask some questions, or, you know, just say hello. Daniel, that's a good question. So the way I would do it, a function is differentiable over an interval if it is differentiable for every point in the interval, right? So if you were talking about a differentiable function on the whole real line, it means for every point on the real line, the derivative exists. If the set is from 0 to 1, every point between 0 and 1, the derivative exists. Okay, so there you go. I think that's the way I think it's commonly defined. Yeah. So let me know if you have questions, people. I know it's been an early morning for some, an hour of algebra and an hour of calculus. So much maths. Don't forget, I am doing a tutorial at 12 o'clock Sydney time. So if you want to come and join us, feel free. So let me know what's happening out there, people. Thank you, Heidi. Shakira. Eric, good to see you, Matthew. Thank you for your questions. Thank you, Vina. Eloisa. Well, Eloisa, that's the definition of continuity, right? We say a function is continuous at a point if the limit and the value of the function at the point are equal. That's actually how we define it. Yep. And that geometrically, that means that I can draw my curve without lifting my pen off the paper. Yeah. No problem. No problem. Have a great day, everybody. If nobody has any questions, I might see you at 12. But if anybody has any questions, jump in. Now is the time. Now is the time. Chen, thank you. Dijant. Aiden, thank you.